Everyone knows how a rocket reaches space. It points straight up, fires its engines, and climbs until it's high enough to be in space. SpaceX's Starship, the largest rocket ever built, sits on a launch pad with 33 engines ready to produce 7,200 tons of thrust for exactly that purpose. Except that picture is fundamentally wrong. Reaching space has almost nothing to do with going up. Starship will spend the vast majority of its energy going sideways, and until you understand why, you don't actually understand what any rocket has ever done. But here's the thing, even going sideways isn't quite right. What Starship really needs to do is fall and miss. Here's the misconception that silently distorts everything pop science teaches about spaceflight. You're told that space begins at 100 kilometers up, the Kármán line. Cross it and you're an astronaut. That's technically true, but it's fatally misleading, because altitude is not the hard part. A relatively modest-sounding rocket can lob a payload past 100 kilometers. The problem is, it immediately falls right back down. What keeps the International Space Station orbiting isn't its height, its speed. 28,000 kilometers per hour of sideways speed. That single insight, that orbit is fundamentally about velocity, not altitude, explains why rockets are shaped the way they are, why re-entry is lethal, why astronauts float, and why the first Starship launch might mark the beginning of the most consequential machine humanity has ever built. Isaac Newton saw this clearly in 1687 with a thought experiment. Imagine a cannon on top of a very tall mountain, firing a cannonball horizontally. Fire it slowly, the ball curves downward, hits the ground. Fire it faster, and the ball travels farther before landing. Now fire it at 28,000 kilometers per hour. The ball is still falling. Gravity is pulling it just as hard as gravity pulls you right now, sitting in your chair. But Earth's surface curves away beneath the cannonball at exactly the same rate it drops. The ball keeps falling, and it keeps missing the ground. Forever. That's orbit, not floating, not weightlessness, not some special state of being in space. Perpetual free fall around a curved planet. And everything about spaceflight, every rocket ever launched, every astronaut who ever floated, every first Starship launch and every 100th follows from this single, beautiful, wildly misunderstood idea. This immediately exposes something almost everyone gets wrong. Astronauts on the ISS float, so obviously there's no gravity up there, right? The ISS orbits at roughly 400 kilometers altitude. At that height, Earth's gravitational pull is still about 90% as strong as it is on the surface. 90%. Those astronauts aren't floating because gravity disappeared. They're floating because the station and everything inside it, every wrench, every water droplet, every astronaut, is falling toward Earth at exactly the same rate. It's identical to the weightless feeling you'd experience inside an elevator whose cable just snapped, except instead of lasting 2 terrifying seconds, it lasts 6 months. The phrase zero gravity might be the single most misleading term in all of science communication. There is gravity on the space station, plenty of it. There is no floor pushing back. And this reframes a rocket's entire job description. A rocket doesn't need to lift you above gravity. Gravity extends effectively forever, weakening with distance, sure, but never reaching zero. A rocket needs to accelerate you sideways fast enough that your falling path curves around the planet instead of into it. Here's where a single number rewires your intuition. Getting to the altitude of the ISS, that 400-kilometer climb, takes roughly 3% of an orbital launch's total energy. 3%. The other 97% goes into horizontal velocity, nearly all of it. When you watch a Starship launch and see the vehicle arc over, tilting from vertical to nearly horizontal during ascent, that's not the rocket turning toward its destination. That maneuver, called a gravity turn, is the rocket finally doing its actual job. The vertical climb at the start just clears the thickest part of the atmosphere. The sideways acceleration is everything. Let that 97% figure sit for a moment, because once you internalize it, Starship's design choices stop looking arbitrary and start looking inevitable. 33 Raptor engines on the Super Heavy booster, 6 more on the upper stage, a combined height of 121 meters, taller than the Statue of Liberty. Practically every headline about Starship leads with the size. World's biggest rocket, world's most powerful rocket. But here's a misconception worth demolishing. Starship isn't revolutionary because it's big. Saturn V was big. The Soviet N-1 was big. Being big is, in a certain sense, the straightforward part of rocket design. You scale up the tanks, you cluster more engines. What makes Starship potentially the most important vehicle in the history of spaceflight is something entirely different. Both stages come back. To see why that's transformative, consider an analogy. A Boeing 747 costs about $350 million. The jet fuel for a transatlantic flight costs roughly $150,000. The ratio is staggering. The vehicle costs over 2,000 times more than the fuel that moves it. Nobody would dream of building a disposable 747 for each crossing. And yet, for 70 straight years, that's exactly what the space industry did with rockets. The Saturn V that carried Apollo 11 to the moon cost approximately $1.2 billion in today's money. It flew once. Its first stage sank into the Atlantic. Its second and third stages were either discarded in orbit or crashed into the lunar surface. $1.2 billion of precision engineering used once and abandoned. The physics explains why this insanity persisted. Remember, 97% of a rocket's energy budget goes to sideways velocity. That velocity comes from hurling exhaust mass backward at tremendous speed. And the Tsiolkovsky rocket equation, formulated in 1903, dictates that fuel requirements grow exponentially with the velocity change you need, not linearly, exponentially. To reach orbital speed, roughly 85 to 90% of a rocket's total mass at liftoff has to be propellant. The vehicle is, by mathematical necessity, a thin-walled fuel container with engines bolted to one end. After the fuel burns, that container is dead weight, which is why, historically, engineers simply dropped it. Bringing the container back means reserving fuel for deceleration, adding structural mass to survive the return, and carrying landing engines and legs. Every kilogram of recovery hardware is a kilogram stolen from the payload you could have delivered to orbit. For decades, the consensus among rocket engineers held that full and rapid reusability of an orbital-class rocket was economically self-defeating. SpaceX cracked the first half of the problem with Falcon 9, routinely landing first-stage boosters on drone ships. But the first stage is the easier challenge. It separates at well below orbital velocity, around 6,000 kilometers per hour, so it doesn't face the full brutality of orbital reentry. The upper stage, the part that actually reaches orbit, does. And here's where another deeply entrenched misconception appears, one that even science enthusiasts and many science communicators repeat. You've almost certainly been told that re-entry is dangerous because of friction. The spacecraft rubs against the air at high speed, generating heat, like rubbing your hands together on a cold day. That picture is wrong in an important way. Re-entry heating is dominated not by friction, but by compression. When Starship returns from orbit at 28,000 kilometers per hour, it collides with the upper atmosphere faster than air molecules can scatter out of its path. Those molecules pile up ahead of the vehicle, compressed into a thin, screaming hot shock layer. The physics is identical to why a bicycle pump gets warm when you push the handle quickly. Compress any gas rapidly, its temperature spikes. At Mach 25, that compression drives air temperatures in the shock layer past 1500 degrees Celsius. In the most intense zones, temperatures exceed 3000 degrees, hot enough to soften or melt most aerospace-grade alloys. This is precisely why Starship is built from stainless steel, a material choice that bewildered aerospace observers when Elon Musk announced it in 2019. Steel is heavier than carbon fiber composites engineers typically prefer for flight hardware. But stainless steel has a crucial advantage. It retains most of its structural strength at temperatures where carbon fiber dangerously weakens. At Starship's enormous scale, using steel means the heat shield and the structural skin can be the same component, saving mass overall. The material that appeared primitive turns out to be the one the physics actually demands. The re-entry maneuver itself might be the most audacious piece of the entire design. Starship re-enters belly first, falling broadside through the atmosphere like a skydiver's spread eagle, using its entire flat underside as an aerodynamic brake. All that hard-won sideways velocity, every bit of the 97% energy investment gets bled off through controlled compression heating against 18,000 ceramic tiles bonded to stainless steel. Then, in the final seconds before landing, the vehicle flips from horizontal to vertical and lights its engines to touch down. SpaceX calls this the belly flop maneuver, which is aggressively casual naming for what may be the most demanding aerodynamic sequence ever attempted as routine. Understanding orbit as speed rather than altitude also reshapes how destinations beyond Earth actually work. Getting to the Moon is, surprisingly, not dramatically harder than reaching orbit. Once you've achieved 28,000 kilometers per hour in low Earth orbit, the overwhelming majority of the energy work is already done. A lunar transfer requires adding about 3,200 kilometers per hour on top of orbital velocity. That sounds significant, but the rocket equation's exponential curve is less punishing when you're adding a modest increment to an already enormous velocity. The energy cost of going from zero to orbit dwarfs the cost of going from orbit to the Moon. Orbit is the summit. Everything else is downhill. Mars changes the calculus not through distance, but through timing. Earth and Mars both orbit the Sun, and the most fuel-efficient transfer path, a Hohmann orbit, requires launching during a narrow window that opens once every 26 months. Miss it, and you wait over 2 years. This is where Starship's reusability stops being an engineering nicety and becomes an existential requirement. If each vehicle can fly dozens of times, fuel tanker variants can shuttle propellant to orbit, gradually filling a Mars-bound Starship in space over weeks. Without reusability, each tanker flight costs hundreds of millions of dollars, and the entire interplanetary architecture collapses under its own economics before a single boot touches Martian soil. There's one more misconception worth addressing, a subtle one that even physics students sometimes carry. The phrase escape velocity suggests a wall. Below 11.2 kilometers per second, Earth grips you. Above it, Earth releases you, as if some force barrier has been breached. The truth is a smooth continuum. Escape velocity is simply the speed at which your kinetic energy exactly equals the gravitational binding energy tying you to Earth. Above that speed, your trajectory opens from a closed ellipse into an unbounded parabola, and you coast outward forever. Below it, you stay bound. But bound could mean a wildly elongated orbit taking millions of years to complete. There's no gate, no wall, just orbits stretching more and more eccentric until, at one precise speed, the ellipse never closes. This clarifies what a rocket truly does. Not breaking free of anything, adding kinetic energy, methodically, precisely, until the trajectory curves the right way. Low Earth orbit is one curve. A lunar transfer is a more elongated curve. A Mars transfer is more elongated still. They're all Newton's cannonball fired a bit harder each time. So come back to where this started. The first Starship orbital launch will ignite 33 engines in South Texas. For a handful of seconds, the vehicle climbs vertically, and every instinct says it's going up to space. But within 2 minutes, it tilts, it arcs, it pours its real power into horizontal acceleration, because orbit was never about leaving gravity behind. Gravity is what makes orbit possible. Without gravitational pull, there's no curve, no freefall wrapping around the planet, no orbital mechanics at all. The rocket doesn't fight gravity. It negotiates with gravity, shaping a trajectory so precise that the vehicle circles the entire Earth every 90 minutes, falling continuously, landing never. Every satellite ever launched, every space station ever crewed, every astronaut who has ever gazed down at Earth through a cupola window, not a single one escaped the planet's gravitational hold. They are all falling. Right now, this very second, the ISS is accelerating toward the ground at essentially the same rate as a dropped coffee mug. It simply happens to be moving sideways fast enough that it perpetually misses. There's something magnificent in that, something almost absurd. Humanity's greatest achievement in space isn't overcoming gravity, it's learning to fall with such precision, such breathtaking elegance, that falling becomes indistinguishable from flight. Starship, if it works, and the word "if" carries genuine mass in that sentence, promises to make that elegant falling cheap enough to become routine. Cheap enough for orbital fuel depots, for 100 passengers bound for Mars, perhaps eventually for construction projects that dwarf anything built on solid ground. But none of that future arrives until the vehicle does something ancient and deceptively simple: tip sideways, accelerate to 28,000 kilometers per hour, and fall all the way around the world. Newton's cannonball, 337 years later, finally forged in stainless steel. And the next time you see 33 engines ignite and that impossible tower begins to rise, you'll know what nobody told you before. The launch isn't the moment it leaves the ground. The launch is the moment it starts to fall. Like if this was interesting, hit the subscribe for more and turn that notification bell on.